Our final speaker is ready to inspire us with a look at nature's most effective engineers. Please welcome Shyalan Ramesh, a software developer and a casual academic at La Trobe University. Beyond his work mentoring students in the GDG community, Shyalan is fascinated by distributed problem solving. And he's here to show us how swarm robotics is moving out of science fiction and being used today for everything from coral reef restoration to critical search and rescue missions. Let's give a huge round of applause for Shyalan.
Thank you, Casey. I think that covered pretty much the introduction about me. So let's not have a lot of repetitions there. So today I'll take you on a journey from how ants and bees and typical other aquatic creatures as well, and also including underwater robots, and how these nature inspiration and bio inspirations could inspire you to the topic of swarm robotics. So the theme is pretty simple today. So the theme is simple rules and having pretty complex outcomes based on them. So getting started. What is swarm robotics? Any show of hands? Have any of you guys heard of swarm robotics before? Yep. Yes. So swarm robotics, in a nutshell, is multiple simple robots together without a central control. So it's not like one massive robot with much complexity versus 100 simple robots together. So it's kind of like a competition between one centralized command and one single robot, one single unit, versus 100 of them, where they don't follow a centralized command. So why does this matter? Why swarm robotics? So it is more scalable and it's pretty fault tolerant. Let's imagine in the world case of robotics where you have like, I'm sure how many of you guys have worked with engineering or CSID? Assuming that's the majority of y'all, CSID. So y'all would have like a lot of like testing errors that do happen, and you would catch like a lot of faults that do happen. And one great thing about swarm robotics is you have 100 swarms out there. They can survive with up to like 10 to 20% cutoff or just disappearing in action. They work. But with one centralized robot, if it's gone, it's completely gone. So that's the key principle behind swarm robotics. So swarm intelligence and swarm robotics are based on nature's inspiration. So we're taking inspiration from nature as a whole, and we're talking in about like ants, bees, and even birds. There are plenty more out there. And for example, when we take about ants, like there are a lot of videos you can see online of people finding how these ants go together. I'm sure you've seen them at home, just a swarm of ants going across the house. And the main thing that you notice about ants, they always find the shortest path between them. And when you think about birds flying together in flocks, which in Australia you see quite a lot of them often, and in those cases, you can see that they always also try to find the shortest path. So these are some common principles between these different types of nature inspiration. And that, as a result, is part of swarm robotics. And we are taking inspirations from all of these, combining together and building autonomous vehicles, aerial drones, drone shows. They're all inspired from swarm robotics. And do any of you guys know that bees also dance? Yes? Have you seen bees dance? No? Okay. So bees it's technically called the waggle dance. So they kind of do kind of like mating as well as whenever they find flowers, nectar, they do kind of have a dance behind that. And one bio inspiration that we gain from that is that it's pretty efficient in sharing resources. So that's also another one. And to summarize this entire key insight into this, is that each agent only knows one local rule. It's not like, as I mentioned earlier, a huge, complex single robot. Each of them individually does only one single task. So they're pretty concise, and they let the group of them together achieve their end result. So where, where do we use these swarm robotics applications in the real world? So we use them in environmental monitoring, to name a few. And these robots act like the coral reef guardians, might I say, because they are continuously sensing what's going on in the environment, underwater, and I'll move further into coral health in the next slide. And these capture these data and they provide them to scientists, which are not possible with typical AUVs, which just goes underwater, swims around, gets typical data, whereas a swarm of them will get a magnitude of data which are easily shareable, easily readable, and has a really good fault tolerance. And as I said, coral reef restoration. So did you know just northeast of Queensland, the Great Barrier Reef, almost the size of Germany, might I add, and one of the researches that they're doing these days is on having these swarm robots release these coral larvae so that they could reproduce and grow more of this coral reef and also protect the damages at the same time. So they're trying to recover what's lost and also expand the coral reef. So this is some of the technology that's helping it and paving the pathway for the future. And these also go with targeted anchoring. So targeted anchoring is where we are having these robots secure themselves onto these Great Barrier reefs and corals without damaging them, so that we're not resulting in any damages to the environment and also helping them grow and gather these data. So search and rescue. So this is something that we've seen now being deployed in Europe, and it's, I think, one of the more, they had a lot of challenges, and surprisingly, it's going pretty well so far. And Swarm is kind of like where you could use them, for example, in collapsed buildings, in floodings. If you have multiple AUVs all under sync and are able to work independently, they can help escalate, they can help find survivors, and they're easy to deploy, and they're pretty rapid as well. And we are not risking human lives at the same time. And as I mentioned over and over again, if one fails or if one gets damages, it's a flood, it's an earthquake, something's going wrong. If one fails, the other can take on the workload and continue. So the power of swarm robotics. So it is pretty scalable. Having 100 robots together working together is pretty a daunting task in itself. And it's like having 100 mini task-specific robot versus 100 1 into 100 complex robots. So that don't communicate together. So that's the reason why we say swarm robotics is completely scalable, and they're pretty robust. There's no central brain. There's no single point of failure. If one fails, majority can take on its workload and just continue. You only lose a point percentile of the data that you're trying to retrieve there. And it's also pretty adaptable because it's sensing and reacting to the environment in like real time. So you can, for example, you're trying to go like object detections and all of those kind of stuff. And it's pretty real time in those sense so that it can avoid certain issues as well. So there are, say, almost like 50 to 100, like this year alone, there are 4 new algorithms that I've read that are pretty popular that came up. And there are like a lot of different algorithms out there, like too many. So there are 3 in here that are pretty classic. One of them that came in the 1990s, something that came up in the early 2000s, 2017s. So ant colony optimization is, as I mentioned, based on ants. So it's inspired by ants. And like I said, it's trying to find the shortest path of a way. And this algorithm is currently being used in Raspberry Pis and Arduinos for uh, a lot of robotic competitions where they're trying to find the shortest pathway between them. And calling optimization algorithm is pretty much leading in that field. We also have particle swarm optimization, which is inspired on birds. So we're trying to explore solutions and trying to find an optimal space for them. And we've also got artificial bee colony, like the name suggests. We're just inspired by bees foraging, and we're finding the best resources for them. Finally, we've got NOAA. So NOAA is a barnacle-inspired algorithm. So it's based on whales. So in this case, I'm sure that you would have seen barnacles in shipwrecks as well, and ships sailing like underneath of them. There are a lot of barnacles, but in this case, it's based on whales. How they are attracted and anchoring onto the whales because they're pretty hard to come off, and you can't just dump them as well once you take them off because they contain chemicals in them as well. So the attraction, how they populate to each other, how they migrate from one to another. So that's the algorithm behind that, and it's pretty unique and new out there. And going to talk more in depth about NOAA. So what does NOAA stand for? So NOAA stands for the Nautilus Optimization for Autonomous Hydrodynamics. Yes, it's a mouthful. The name behind it, I think it's just because NOAA, aquatic, sounds nice. So yeah, and this algorithm, as the name suggests, it's more focusing towards the hydrodynamics behind it, where we're using water currents for movement, and we're also checking in on the settlement anchoring because we want to have these barnacles be permanent, follow a permanent behavior, as well as colony field computation, because we want these swarms to be pretty efficient as well. And some of the impacts of these are done in a lot of case studies related to reef monitoring. And there are also some assisted navigations, especially in the underwater environment. And we could also help with pollution detection as well. So those are some of the three key impacts in this field. And if you have noticed, you can see like how different animals, like for example, ants and bees, birds, whales, they all focus on different categories. Some are focused on aerial, which is why we have drone shows now after those algorithms. Some are focused more towards underwater exploration. So there are different use cases for them, and they all link back to use cases on search, underwater exploration, and many more. So the simple rules behind any swarm optimization or any swarm robotics is to avoid collisions and to have a pretty good safety net between them so that they don't collide with each other. And we also want to align with each other's neighbors. That way they're pretty coordinated for direction. That way they can move from one spot to another without colliding with each other and navigating smoothly. And we want to have a group cohesion, which is why we move towards targets to reach our end goal. As a result of this, we have flocking, clustering, and exploration, which emerges without having a dedicated leader. So, hardware platforms. There are quite a few load of hardware platforms out there, and there are modular AUVs, underwater drones, even wheel-grounded robots and drones, to name a few. And we have quite a couple tons of sensors, including sonars for mapping. We have acoustic sensors, biodiversity monitors, cameras. There's a huge ton of them. Like pretty much here, everyone has worked, assuming at least with one type of sensors with Arduinos or even with Raspberry Pis or something, or even your phones, for example, even my microphone, for example, one, or this camera which is recording me somewhere. So yeah, all of these are part of sensors that we use in swarm robotics. And we are overcoming a couple of challenges as well. Communicating underwater, for example, is pretty difficult compared to communicating up on air. The two different fields. There are a lot of limitations between that. and it's pretty slow, pretty noisy, and energy, for example. How do we get these batteries to last longer? Like my phone battery sometimes dies just after I don't know, a day's worth of full usage. So, how do we get these autonomous robots to work? And we're talking about hundreds in a large scale. How do we get them to work efficiently and also to move from one swarm to another and do all of the tasks dedicated without just dying out? And lastly, it's also towards scaling them. Scaling them is also a pretty significant issue. And moving on to simulation and development. So just before I start on this, how many of you guys have seen this video just on the side? That's good. So this, to the ones who do know, is a collaboration between NVIDIA, Google's DeepMind, and Disney Research. It looks like pretty much like Star Wars and Trek. So it's a good collaboration between the three, and they've come up with a really good hardware and simulation development models between the three. And the development model is called Newton, and they use that to develop this robot. And you can see glimpses of the software being used as well. And these tools, including additional tools like Python, ROS, can help with control and communication. Additionally, we can use something like Unity and Gazebo to simulating it in realistic environments. How many of you are game developers or have worked with one or two of Unity before? So you know how realistic you can add to physics and to the meshes and how realistic simulation can be between them. So that's one of the tools we use. And for hydrodynamic modeling, we kind of work with accuracy with them. So we are simulating drag, turbulence, currents, and this mostly works out with aerial and underwater rather than over the land. And finally, performance metrics. So how do we calculate these data? How do we analyze these results? So these results are based on convergence, robustness, and scalability. So how much area has been explored? How well has this swarm communicated and done its job? And how well of a failure ratio do we have? And how would you calculate the performance of larger swarms? So that's basically summarize simulation and development tools. Moving on to this. So this was generated with a complex code with Python. And as I mentioned, we're trying to see between different models mentioned here and 14 different simulational algorithms out there established, how these swarm robotics and swarm algorithms compare between the 14. And as you can see, we've got two pretty much further away, and something like particle swarm optimization, which is the one over here, ABC and DE are pretty efficient. They're pretty good. They're like in this under a second. And these different tests are taking into account movements, placements. Towards the end, we're talking about anchoring, as well as how it's going to work under ocean currents. So it's testing different segments of them throughout. And you can see most of them are quite sufficient. They do the depth. And I would say one problem I would find with this result and these data is out there is that we're not taking into account, like, for example, in this case, some unexpected situation and how in-depth the exploration is, how clear is the data that's being extracted is. So that's one of the limitations behind this. So since this is a Google Devfest, as previously mentioned by the last speakers, there are some great, amazing Google technologies out there that help us do this. So TensorFlow, how many of you guys have worked with at least one of these technologies? So it's a majority. That's great. So TensorFlow. So with TensorFlow, we can pretty much help to train and adapt these behaviors of these swarm robotics models. And with Cloud IoT Core, we can have like fleet management, and pretty much it could be the heart of the system as well as maintaining some secure communication between them. And Earth Engine, which I think Andrew mentioned as well at the start of the Devfest this week to today, and it's a great engine for satellite imagery and also environmental data for mission planning, because these data is synced together and it's great for mission planning. And an example of a combination of all three together would be back to my use case 2, where we're having a reef restoration mission plan, and using all of these technologies together, we can help with live environmental monitoring and behavior analysis. So swarm robotics goes beyond just robotics. We can learn from that as developers ourselves. You know, we can learn to do system thinking. We can think like how these robots are meant to think based on these bio-inspirations. You know, we're viewing agents and swarms as in an environment as a whole. You know, and we're learning about how to collaborate, and as well as leadership, as well as no one-point failures. And you know, we're developing this in teams, and we're working towards one end goal. And all of these could be ideas and points for developers such as ourselves to learn from. And as well as finally adaptive communication as well. We're explaining robotics to a more diverse group, and you know, not only just engineers, policymakers, software developers, and even communities. So it goes beyond robotics. It goes beyond the general views, and it's more nowadays as well focused towards education in the schooling sector as well. So ethics and sustainability. So we need to make sure we're pretty responsible with the deployment, and we don't want to damage, like in use case 1, damage the Great Barrier Reef. No, I don't want to get in trouble. Let's try to protect these fragile ecosystems and data privacy. We need to protect the biodiversity of our data, and we don't want them to be lost or stolen or damaged. And we need to make it accessible. It needs to be free, open source, and available to all developing nations, these algorithms. And surprisingly, some of these algorithms cost a pretty penny, while the majority are free, but the ones that work with real world scenarios are pretty pricey. So, you know, we would like to see movement in the industry to have it open source and also make it available to all developing countries. So, I think we're almost out of time, I believe, but almost there. I know it's been a long day. So, future directions. Where can we move on from this? So, currently, some of the limitations I mentioned earlier were going beyond 100 swarm robots are pretty hard. So, reaching about 1,000 should be the next goal. That way, we can have like thousands of micro robots working in sync together without a centralized command to explore the uncharted, as well as in search and rescue. And AI integration. So as we started Devfest today, AI is a growing field, and it's not going to die out anytime soon. So we can focus on combining large language models with swarm intelligence. Imagine an AI that's able to mimic human behavior as well as bio inspiration from these nature derived animals and creatures, plants, nature, you name it. So combining all of these with AI will bring in a new scope of discovery within AI. And also, finally, you know, we need to have a different type of partnership as well between the industry, government bodies, and a lot of academia involved as well. So, in summary of my huge presentation today, simple rules equals complex power. We want all of these swarm robots to do simple tasks, but collectively, they bring out a strong work together and a completed results. And these bio-inspired algorithms, they need to be robust as well as adaptive. We need to have some really strong real-world impact where environment, restoration, and rescue is also considered. Finally, as a Google event, we need a lot of these Google technologies, as well as the upcoming Gemini with AI for robots specialty. All of those programs and all of those models will allow us to continue this into further. Before I conclude, I have a QR code here. This QR code will help me if you guys have any other suggestions, any ideas, and anything you like or would like to see more towards swarm robotics or the turning point you see. you can feel free to put in some details relating to that. That way, hopefully share this with the academia world and see how we get more results from that. So everyone's done with that, and that's it. Thank you. Uh, Feel free to ask me any questions, and I'll hopefully try to answer some of them if you have any. Yeah.
Nice presentation. Nice to see that your technology is nature inspired. So what I want to ask you is that nature also has some faults and some unexpected effects, mainly towards diseases. Let's say your swarm of robots is contaminated and some of the robots are going rogue. How are we gonna contain that? How are we gonna isolate that? What's the approach towards that? And I'm saying that especially if you have, let's say, a million robots on the Great Barrier Reef, and all of them go rogue. What's the situation? What's the approach?
That's a really good question, and that brings in a strong point on cyber security side of things. Firstly, it's highly unlikely for all of them to go rogue. That is a use case because they're all individual. There's no centralized command. So they're all working independently. So if you're talking about 1 million, yes, let's take hypothetically in a scenario where 1 million goes. That's an area in the world where there is not much research in, since this is a developing and emerging technology. What we can do, I see, is having a kill switch that whereas the code gets corrupt or someone breaks into the code, that way we can have it as a kill switch. But this is more like a decentralized platform where you need to swarm back together, then only we are able to retrieve it. So there is no communication from the user or network communication to the swarm. It's the swarm doing its own thing and getting back to us with this collective data. So we're not having a live interface where we can do all of these things. And that's one way we're keeping these models offline, preventing hackers, preventing data changes. But if there is a scenario where it comes up, and I think it could possibly in the future, I'm sure technologies grow, they'll find something that could break into a system that is completely offline. Well, there are a few, but in robotics context. But yeah, it's a good question. And the solution for that is not yet there. Any other questions?
We've got a question at the back. I'll just take the microphone.
Thanks for a great talk. I was just wondering, do you collect telemetry in a form that would be usable to then use as part of training sets for future models?
Yeah. Yes. So we collect all of these data so it's based on iterative, and I think these bio-inspired algorithms, before they are where they are now, it's based on these kind of similar to how AI models were trained initially, where you're feeding it large data sets and then you're training it as it goes on. These models are based on how you see how I think it first comes up with first dedicating an algorithm to it, and that's not fully correct, not fully functional, and then you start simulating them, and then basing on how these simulations perform, you do it in real world. And simulation to real world, not always the perfect performance, pretty bad sometimes. And then we collect those data, and then we start building again and revising and revising. And those data collection helps us identify how successful the optimization is between the swarms. Yeah. And how do I know this? Because we created an algorithm that is simulation here, real world here. So we need to start training it furthermore and try to make sure the algorithms are perfect. So yeah. Okay. Any other questions?
So for the example, by the way, great talk.
Oh, thank you.
All the examples were related to the nature and other things. What are some of are there any military and other things which are happening using these?
Yes. Oh, sorry, Carl. So the NOAA algorithm is something that we created, and it's still in testing phases. And it's something that we even pitched to ADF. So it's something that the Navy can use for coastal protection. there are a lot of use cases because it's underwater. The Navy could use it to protect its resources and protect Australia. So that's kind of like a pitch towards that. And not only in terms of defense or protection, there are also a lot of entertainment usage, as I mentioned, drone show, mentioning drone show because there's one coming up in Sydney soon. So should possibly go for that. But those are all based on these different algorithms collected together, and then they have their own data set and all algorithms for it. So yeah, any other questions, anyone?
What would your advice be for hobbyists interested in swarm robotics? How do we tinker at home? Where do we start?
I would say start with particle swarm optimization because that's the easiest. And I believe there's quite a ton of kits already online. You can just go to Amazon. I think, yeah, Amazon's the best place. There are a lot of kits to get you started. And there are even like, for me, what got me started and hooked on to these swarm optimizations in general was the drones. Because there are kits which I got quite a long time ago, where there's mini quadcopters, multiple of them, and where you can sync their movements and do exploration. And those kits, and there are even detailed YouTube videos on how you can construct them from the kits, and then how you code them, which algorithms you're using, and all of them are available. And I think PSO, particle swarm optimization, is the easiest of them. And you could also, from there, navigate to different algorithms, as you see. It's always experiment and see. For me, it was PSO. For someone else, I've met with other scholars from Monash recently who said that for them it was ant colony optimization, and they absolutely hated PSO. So it's a personal preference. Yeah.
Any other questions?
Thank you. Great presentation.
Oh,
It's
thank you.
always impressive how Ant and Bee works as a team. I might get it wrong, but from my assumption, I think that swarm robotics enable every worker to be able to perform every single task. And if that's the case, and what is the performance compared to having some specific workers perform dedicated task compared to this swarm robotics use case?
So I think there is something mistake with that. Actually, swarm robotics, to be honest, is more towards individual nodes, so individual AUVs doing one dedicated task, not a collective of them. So a swarm robotics, let's say we have just this room, for example, we release like, I don't know, maybe 10 to 15 UAVs here. And let's just say one is going to do scanning, one is going to do temperature, because each of these mappings are going to have different regions. So they all follow the same track or swarm around, but they're all collecting different data and they all overlap each other. So that is one take on swarm. Whereas there's another take where there's an argument where each individual node should have at least, all of them should have one basic common principle, which is, I would say, mapping or temperature or something, and then have another uniqueness to each of them in terms of sensory data collection. That way there is a differential, and that way the collected data is more accurate because there's multiple swarms collecting one or two of the same data.
Thank you.